Right. So last class we did orbit determination, right? We did Gibbs method of orbit determination. Have you guys started working on the MATLAB assignment? You have? If you need help, you can always ask me, okay? All right. Let's try to do ground tracks. Okay. See, one of the very important things about a satellite is ground track. You understand what do you mean by ground track? Huh? Say that again. Yeah, you can say that. If you try to describe the problem, without getting too technical. See, Earth is rotating, right? And the satellite is also rotating around the Earth. And you can imagine or can visualize these two. First of all, these two are not rotating at the same period, right? Earth's rotational period is, Huh? 24 hours. And the satellite's orbital period is a function of It's not a function of Earth. We discussed this, I think, but you guys have again forgotten. The Earth, it depends on the position of the satellite, the R vector. Okay. So what does Kepler's second law say? Huh? You have Kepler's second law? Sorry, Kepler's third law. The orbital periods, if you look at Kepler's law, period is proportional to cube of the distance, right? The square of the orbital period is proportional to cube of the right. So you can say 2 distance cube. So this actually gives you the relationship between orbital period and the distance. Okay. So this t square is equal to q. All right. So what does this tell you about the orbital period? Does it mean anything? What does it mean?
It means that you figure out if you know the distance of R, and you figure out just the order of period of how long it's going to take.
Anything else? What does it mean in the context of of ground tracks. That was the reason we brought this up, right? If you look at this, the farther an orbiting body is, it has a bigger orbital period. Okay. So if you're looking at, you've heard about geostationary or geosynchronous orbits? Geosynchronous orbits? No? Not heard about geosynchronous orbits? Heard about GPS satellites? You heard about your dish satellites? So dish satellites have to stay, the relative position of the dish satellites has to be, it's not the pointing, it has to stay there. It cannot move around, right? Otherwise you are going to lose your signal all the time.
So it follows the direction and speed of the sun. Not the sun, but the earth. Like as the earth rotates, it rotates with it, so it seems stationary.
Right. You cannot say speed, you should say the orbital period of these dish satellites is the same as the not the orbital period. Orbital period of the Earth is 365 days. The rotational, the amount of time Earth takes to complete one rotation. So if it is rotating, if it's doing that, if you put the dish antenna or the dish satellite far enough, it will rotate at the same period. So the relative position of the dish is always fixed. You're always able to see that. Even your GPS satellites are geosynchronous. The geo means Earth. Synchronous means it synchronizes with the Earth's rotation. Right. That is a very specific distance. It has to go a very specific distance because it's actually directly proportional to the period. Okay. So what is the orbital period of Moon? Do you know what the orbital period of Moon is? Huh? 28 days. Yes. So the orbital period of Moon is 28 days, and that is one of the ways to keep track of time, your not what time of the year, your month is based pretty much on the orbital period of Moon. Okay. Your year is based on the orbital period of Earth around the Sun. Okay. Seasons are based on Earth around the Sun. Your months are based on every 2 weeks. Your moon becomes a new moon, and every 4 weeks the moon becomes new moon and a full moon. Right. You have to understand what is full moon, what is new moon, what is new moon, what is full moon. Right. So where is the moon at that point? It is not because of the shadow. That is an eclipse. If it's because of the shadow, it's an eclipse. Okay. So if you have Earth, right? If the moon is here and the sun is here, okay. So all the light is falling here, right? So this part is dark. That's when it is new moon. Okay. When the moon is here, all this is illuminated. All this part is illuminated. Right? That is the full moon. Okay. So this is your crescent moon. This is your crescent moon. Because see what happens here is only a part of the light is reflected back onto Earth. Okay. So that is the reason you see the if you keep a track of the moon these days, you'll actually see the crescent and the other part as well. Okay. Now, looking at ground tracks, the reason we brought this up is ground tracks can get really complicated, okay? Especially if the satellites are in low Earth orbit. Your Earth is rotating in a particular direction, okay? So let's say this is your Earth. It's rotating about this axis, right? The axis is inclined by a certain angle. The axis of rotation is inclined. The equatorial plane, this is the north-south, and this is the equatorial plane. Okay. So the axis of this is the north-south direction. North-south direction. North-south. North-south, okay. So this is the axis of rotation, right? So the axis of rotation and the ecliptic plane or are not the same. You understand that, right? Actually, this is the equator. The equator is not the equatorial plane and the ecliptic plane of Earth are not the same. They are inclined. Okay. Anyways, so if you're looking at this Earth, your satellite could be in this orbit, right? It could be in this orbit. It could be in this orbit. And it could be here or it could be really far off. Now, if you want to keep a track, you really need to know the orbital period and the exact position vector of the orbiting body at every point. Okay. So, how do we calculate the ground track or It essentially means when the satellite is going to be overhead your particular location, for your particular location. No. Orbital period is the time taken to complete one orbit. That is a misunderstanding you have. If the Earth was still, you would see every time you would see the same. You would see the same this thing. Okay. So something is rotating. If you're standing still, you can see that. But if you yourself are rotating, it may take more time for you to see that, right? And especially if you're, see if the inclination of this orbit is not zero, then it will get even more complicated. You see that? Because if you're rotating like this, and if the orbit, if you're rotating like this, okay, the Earth is rotating like this, and the satellite is also orbiting in the same plane, then you can just subtract the time you're rotating and the orbital period. Then you can see it every orbital period minus or plus that time. But if you're rotating like this and the orbit is like this, and it will start getting more complicated. Okay. So one of the things we learned was when we did coordinate transformations, recall geocentric equatorial frame to right ascension declination frame. Okay. Let me bring up the coordinate transformation so that you guys have a I don't think this computer has that information. Anyways, so do you remember this geocentric equatorial frame to right ascension and declination frame transformation? You don't remember. Do you remember the frames? Do you know what these frames are? IJK, right. IJK, or you cannot say IJK. The geocentric equatorial frame is your ECI frame, right? Earth-centered inertial. So your x-axis is pointing to Aries, right. So the X is pointing to Aries, right? Aries constellation. And what is the other direction? don't have to say North Pole, you can say the axis of rotation. It's the same thing, but it's more appropriately axis of rotation, okay? Or and how about this one? The right ascension and declination frame. So the right ascension and declination frame, which is, you can also Lat-Long frame. Right? This is the, you have the meridian, right? And you have the equator. If you're going from the equator up, it is declination. Okay, or it is latitude. Okay, the right ascension is the longitude. So you have the 0 degree meridian, right? If you're going right, it is, you have 1, 2, 3, whatever degree, that is the longitude. The transformation we saw for this one was you have R expressed in terms of x I plus y j plus z k. Okay. What frame is this? So the ECI frame, IJK components, right? So this is expressed in ECI. So what did we say? You can write R in terms of R, U, R, right? This is the magnitude, this is the direction. Now, U, R would be equal to Li plus Mj plus N. Okay. And this is equal to cosine delta cosine alpha I Now, try to get an idea, try to get a sense of what we are trying to do here, okay? How would, Sammy? So look at this. See, does this make sense? Try to think about how would you go about actually tracking your satellite, okay, as time passes. Now, when we say ground track, when you say ground track, you actually develop something which will continuously track it as time passes. Okay, it's like can you keep a track of airplanes when they are going? How do you keep a track of airplanes or aircraft? You can use GPS. Can you use GPS to track your satellites? Huh? No, can you keep a track of your satellites using GPS? See, when these GPS, when you sitting in the aircraft, you can track where you are. Okay? But the aircraft itself, if you want to track where that aircraft itself is, from your control center or command center or the control room, the air traffic control room, how do you do it? You send that signal, right? To send that signal, what do you need? For example, you need a line of sight. Line of sight. Correct? You need a line of sight. You understand what line of sight is? It's just line of sight. It has to be able to see something. Okay? It doesn't necessarily have to see a satellite. It can see another ground station, right? For example, that can be your cell phone towers pretty much work on line of sight principles. You are not always communicating with the satellite. Okay? So aircrafts need that line of sight to transfer that signal, correct? If you're talking about satellites, the satellite itself may be able to track itself using GPS. But how is it going to send that signal back? You need a receiving station on the ground, and it has to be in that line of sight of that receiving station. Correct? If it is not in the line of sight of that receiving station, a satellite is as good as lost. Right? You can do that, but there should be people willing to take that signal and send it to you. They should know which satellite that signal is coming from. They should know where to communicate. If it is very critical, you cannot rely on somebody else sending that signal to you. Right? It may be transmitting a signal, okay? But only that signal is received only if something is in the line of sight. So what you do is, let's say you do a radar on the satellite, okay? Now, you do a radar and you figure out this. You figure out the position at some point, okay? You figure out the position and you figure out the velocity as well. You can do that, right? X dot I plus Y dot G plus Z dot G. Okay. Now, if you know the position and velocity, you can use just, if you, for a given position and velocity, you can just use mathematics to keep a track of where it is. Okay? So, for example, if you, let's say you know this, okay? You can calculate the declination, which means you can calculate the longitude. This component can be calculated, right? You just equate this one to this one, or equate this one to UR, or equate this one to N. You will know the declination. If you know the declination, what does it mean? It means you know the appropriate longitude, right? Longitude on the Earth, and your longitudes and latitudes are marked on the Earth, in the sense you know where each latitude and longitude is. You know every place on Earth, the latitude and longitude of every place on Earth, right? So you know the longitude, and you can use either this one or this one to calculate the latitude, right? So if you just keep a track, if you just write a script, okay, because you know the position and velocity, you will know how it is going to go, what are the orbital elements. We did that, right? So you know the orbit, you know the orbital period. You can write a simple script to figure out as and when time passes, what is the longitude and latitude. Okay? And you can say, if the longitude and latitude is within your sight, is within your reach, you can say, if you know the time, you can do the script ahead of time. Okay? And you can say, okay, I know it is going to come overhead at this particular time. So let me point my antennas in that direction and try to receive what it is sending. Okay? So this makes sense? You cannot quite do this with aircrafts, okay? Because, see, when we talk about satellites, we are mostly talking about Keplerian motion. At least in this course, we are talking about Keplerian motion, which means gravity is the only force acting on the satellite. Okay? The motion is very predictable. When gravity is the only force acting, the motion is very predictable. Aircraft is propelled, right? It is very precisely propelled. Unless you know the information, the propelled information, you cannot do something like this. Correct? See, even with so much advanced technology, we lost the Malaysian aircraft, MH17. Correct? Yeah. You wouldn't lose a satellite so easily. You could lose, but you can do. In fact, every object in space is actually being tracked in real time. If you send something out there, somebody will identify and say, look, there's something new. They know that precisely. Okay? Yes.
Going back to what you were talking about, the line of sight, is there a specific range that it has?
It depends on the signal, the output signal, and there's something called Well, it depends on the strength of the signal. For example, you know AM and FM radio, which is more powerful. AM is more powerful. So AM can reach out really far. So there are essentially the carrier waves. There are the actual data, and then there are carrier waves which carry the data. So it depends on what those carrier waves are, how strong those it's like sound, right? So the bigger the sound at the source, the farther it is going to go. Every signal attenuates, right? It reduces in strength. So whatever you can generate at the source, and also it's a property of how good your receiver is. For example, all of us don't have the same hearing capacity, right? Some of us can hear better than others, and there are hearing aids when you talk about which can hear really small signals, right? So it's a function of the source and the sink. If you have a really neat antenna, a very nice antenna, you can sense even very faint signals. Okay, there's something called link budget. Okay, if you happen to have the time, look up this link budget. Link budget is essentially, whenever you launch a satellite, you know the altitude of the satellite. You know what altitude that satellite is going to go, right? When you're designing the receiver, the transceiver on this satellite, you calculate the link budget. So when the signal comes from the satellite to the ground station, it goes through different layers of atmosphere, right? And you have to calculate the losses it's going to experience when it goes through those different layers, and make sure whatever source you're generating and whatever sink you have at your disposal, the source and sink are enough to receive and send that signal. When it goes through, see, you cannot change what is in between, right? You cannot change the atmospheric layers. You can either change the source or you can change the sink. Again, the source and sink change. If it is receiving for the satellite is the sink. If it is transmitting for the satellite, it's the source. Okay. So more often than not, the ground station does not change much, because you can put a more powerful receiver or a transmitter on a satellite, but you don't want to change your ground station equipment too much. Correct? You don't want to get an entirely new antenna system or a new amplifier. Right? All right. Can you please give me your attendance? So what I'll do is I'll send you. Hang on, Lowell. I have something. I'll send you an assignment today, which will involve Gibbs method, ground tracks, some assignments for the previous material we have covered. So your midterm included chapter 1 and 2, right? And we have done chapter 3 and 4.